In the previous video, we went over how action potentials are generated and the steps involved. In this video, we're going to look at action potential transmission. So once you've generated the action potential at this axon hillock, how does that action potential move down the axon to stimulate the release of neurotransmitters at the axon terminal? That's what we're going to focus on in this video, is how action potentials are transmitted along the membrane. When you look at the transmission of an action potential or the propagation of an action potential, what this allows is communication from the axon hillock to the axon terminal. Once this axon hillock is depolarized to threshold, then voltage-gated sodium channels are going to open, and sodium is going to flow into that axon. This resulting inflow of sodium ions is going to depolarize the adjacent membrane to threshold. So remember, we know that when sodium comes in through those voltage-gated sodium channels, you have the depolarization phase. This is where it's going to depolarize to positive 30 millivolts. That sodium that's coming in is going to diffuse in both directions. And then that sodium is going to go to the next voltage-gated sodium channel. And when it does this, it's going to take that next voltage-gated sodium channel from minus 70 to minus 60 threshold, and it's going to open. And you're going to have another depolarization here. And then, of course, you have potassium channels opening right after that, and that's going to give you a repolarization. This resting membrane potential of minus 70 is actually all the way down the axon. And each of these voltage-gated sodium channels are at that resting membrane potential. But when the preceding sodium channel opens, sodium's going to come across, and it's going to bring the next voltage-gated sodium channel to threshold. And it's going to open, and it's going to depolarize as sodium moves in. And then that sodium is going to move by diffusion to the next voltage-gated sodium channel and take it from minus 70 to minus 60 threshold. And then that one opens. And this continues on all the way down the axon. So when you look at this action potential diagram where you have a depolarization and a repolarization and a hyperpolarization, this is for every few sodium-potassium channels along the membrane. So you have multiple spikes all along this membrane as this wave of depolarization, this action potential, moves along the membrane. So the sodium shown here is going to bring the next voltage-gated sodium channel to threshold. It opens, sodium comes in and brings the next one to threshold, all the way down that axon. And then following it is going to be the repolarization. Because once that sodium has come in and it's gone to the next voltage-gated sodium channel, following that you have repolarization, potassium moving out. And that's what this is showing right here. By the time the voltage-gated potassium channels open and potassium moves out, that next voltage-gated sodium channel has already opened. That's the way you get an action potential from one end of the neuron down to the other end of the neuron. Or the muscle cell membrane, where you see the muscle cell, it's going to behave the same way. You have voltage-gated sodium-potassium channels, and those action potentials are going to move down that muscle cell membrane in the exact same way. So looking at our diagram that you have in your notes, you have these voltage-gated sodium-potassium channels, and one thing to note is that I have these voltage-gated sodium-potassium channels on one side of the membrane only for simplification. This is a three-dimensional axon. And these voltage-gated sodium-potassium channels are all around that axon. I'm just showing them on one side just to make it easier to see. And then also your sodium-potassium pumps. It's not that they're on one side of the axon. They're all around that axon on the cell body and so forth. I'm just putting them on the bottom here just for simplicity so it's easier to see. That action potential travels all the way down the axon. Voltage-gated sodium channels open, sodium moves in, and that's what you see here in this animation. And then right after that, you're hitting positive 30 millivolts. That's going to open up the voltage-gated potassium channel that's right next to that voltage-gated sodium channel, and it opens and you have repolarization. This happens all the way down the membrane. Once you get to the very end of that axon terminal, again, here we have a skeletal muscle, and you have your synaptic end bulb that has vesicles containing acetylcholine. There's voltage-gated calcium channel. That change in voltage of sodium coming in here through the voltage-gated sodium channel is going to raise it to positive 30 millivolts, which is the voltage that opens up the voltage-gated calcium channel here at the synaptic end bulb, or the terminal bouton. That calcium comes in, it stimulates the release of these vesicles containing acetylcholine. Acetylcholine is going to go across the synaptic cleft. It's going to bind onto the acetylcholine receptor, which remember is a ligand-gated sodium channel. Because the ligand is acetylcholine, it binds to it. Sodium is going to go in. That's going to take this resting membrane potential, which in a skeletal muscle cell is around minus 85 millivolts. That's going to take that to threshold, and when you hit threshold, that's going to open up a voltage-gated sodium channel on the membrane of the skeletal muscle. And then that sodium is going to come in, it's going to diffuse across and open up the next voltage-gated sodium channel, and then potassium is going to move out right behind that, just like we saw with the axon. So what you've learned in the axon of a neuron and the way it sends action potentials is exactly the same way that those action potentials move down the sarcolemma or muscle cell membrane. And at this neuromuscular junction, we have our acetylcholine esterase that'll break down the acetylcholine. So everything that's happening here at this neuromuscular junction is happening here at the neuron to neuron junction. The exact same mechanism for generating and transmitting an action potential. Well, all of this sodium and potassium moving in and out as you're opening up voltage-gated sodium channels, voltage-gated potassium channels, and it might seem like this is a tremendous amount of sodium and potassium that's moving through, but in actuality, it's a very small amount of sodium and potassium. Since that resting membrane potential is just at the membrane, that minus 70 millivolts, it doesn't take a lot to raise it from minus 70 to threshold, and then threshold to positive 30 millivolts. So not a lot of sodium is coming in, and not a lot of potassium is leaving to repolarize it. But with this sodium moving in and potassium moving out, you have to have a way to reestablish the concentration gradient. Because if you didn't have this, if you didn't have a way to reestablish the high amounts of sodium outside the cell, high amounts of potassium inside the cell, then eventually you wouldn't have a concentration gradient for sodium and potassium to move down in the generation of an action potential. So what is it that helps to keep sodium high outside and potassium higher inside? The sodium-potassium pump. It reestablishes the normal ion concentrations and gradients, and make sure you have this. For every 3 sodiums pumped out of the cell, 2 potassiums are pumped into the cell, and ATP is used to generate that. And we'd gone over the details of this earlier on, but you want to make sure you realize you have these sodium-potassium pumps all over the neurons, all over the muscle cells. In fact, every cell has sodium-potassium pumps. Even though not every cell is going to send action potentials, every cell uses this concentration gradient in its normal function. So the sodium-potassium pumps are absolutely essential for normal function of the cell. And it uses a lot of ATP, or adenosine triphosphate. What happens when you get to the very end of the axon? Well, we'd gone over this previously, and this is exactly the same as what we talked about with the neuron-to-neuron junction. Your action potential comes down, it opens up voltage-gated sodium channels on that neuron that's innervating a skeletal muscle. The acetylcholine-containing vesicles release their acetylcholine by exocytosis, goes across the synaptic cleft. Acetylcholine binds to the acetylcholine receptor, opens it, sodium comes in, and if there's enough sodium coming in to reach threshold, you fire an action potential along the sarcolemma, or muscle cell membrane. Let me ask you this. We know along the membrane right here we have action potentials, voltage-gated sodium-potassium channels. What type of potential is generated right here as that sodium comes in through this ligand-gated sodium channel or acetylcholine receptor? And the muscle cell, it isn't an action potential, it is a graded depolarization. And if there's enough sodium coming in that graded depolarization, it'll bring the muscle cell membrane to threshold and fire an action potential all along that muscle cell membrane. All right, let's test your knowledge. Now, these questions are covering the previous video on action potential generation, as well as this video on action potential transmission. So pause your video, answer the questions for part 1 on action potential generation. Here are the answers. Pause your video and answer the questions for action potential generation part 2. Here are the answers. Part 3, action potential generation. Pause your video, answer the questions. Here are the answers. Part 4. Pause your video and answer the following questions. Here are the answers. This is action potential transmission. Pause your video and fill in the correct terms. Here are the answers. This is test your knowledge, restoration of the sodium-potassium cell levels. Pause your video and explain the following. Here's the answer. Here you're going to test your knowledge on labeling the graph of an action potential and explain what's happening at each of these numbers. Here are the answers. And that concludes this video, and let me know if you have any questions.